today I'm going to present on my research on decadal resistance and resilience of Los Angeles' urban vegetation in response to drought and temperature stress. So this is essentially summing up the presentation itself. So I'm looking at how vegetation in Los Angeles responds to stress. So this here is Los Angeles in the context of Southern California, which is what I'm looking at. And for the outline, I'm specifically going to talk about urban ecosystem services and how stability plays into this in terms of resistance and resilience. I'm going to talk about my research goals, my methodology, my results, and I'll conclude with some challenges they face in doing this work, as well as some recommendations for future research. So cities derive millions to tens of millions of dollars in benefits annually from urban ecosystem services. The U.S. Forest Service estimates that Los Angeles derives at least $52 million per year annually from urban ecosystem services provided by the urban forest. These services include such things as water filtration, carbon sequestration, removal of air pollutants, and the reduction of the urban heat island effect. However, the continued provision of these ecosystem services is contingent on urban vegetation remaining healthy and productive during times of stress. So understanding how a vegetation responds to stressful conditions is important for the continuation of ecosystem services during stressful conditions. Understanding the dynamics of vegetative stress can be understood through the concept of vegetative resilience or stability. Urban ecosystems in particular are unique to plants and uniquely stressful for plants because of such things as high impervious land cover, high levels of pollutants, and expected impacts from climate change. Just last Monday, a paper in Nature Climate Change warned that some cities may face up to 14 degrees Fahrenheit additional warming by the end of this century due to combined effects of climate change plus the urban heat island effect. So understanding how cities and plants in cities respond to stressors such as these can be understood through the concept of vegetative stability. Stability itself can be broken down to resistance and resilience. Resistance refers to vegetation's ability to withstand stress and to maintain function under stressful conditions. The vegetation itself wouldn't change function until it reaches a threshold or a tipping point or a critical threshold, after which the vegetative response can change dynamically. Resilience refers to the ability for vegetation to recover pre-stress levels of function after the stress is removed. So vegetation that is highly resistant won't change function under stressful conditions, and vegetation that is highly resilient will be able to quickly recover function after the stressor is removed. So to study the dynamics of how urban stability, or how the vegetation of how the stability of urban vegetation is influenced in Los Angeles, I tested two hypotheses. First, I tested the abiotic variability of drought and temperature throughout Los Angeles. This can be considered as looking at how the microclimate of Los Angeles affects stability. I hypothesized that increasing variability in microclimates, so there's more spatial variability in temperature and drought, would decrease stability due to extra factors that the plants would continuously need to adapt to, as opposed to plants that are in more homogeneous environments. For my second hypothesis, I tested the effect of income on stability. The luxury effect says that areas that are more affluent or that have higher income are generally more species rich, and as well have a higher provisioning of ecosystem services. The literature also says that areas that are generally more species rich may have more stability of their vegetation. So I would expect that areas that are more affluent would also have more stable ecosystems. So to look at this, I looked at Los Angeles from 2000 to 2016, from June through August. I was looking at the political boundary of Los Angeles minus the large parks because I was interested in just how the urbanized section of Los Angeles specifically responds to stress. This here is an image of NDVI from August 20th of last year. NDVI plays an important role in my project and stands for the Normalized Difference Vegetation Index, and it's a proxy for plant greenness or plant productivity. Plants reflect sunlight in unique ways, allowing vegetation to be identified remotely using satellites such as Landsat 8. In this image, everything that's green or that has high NDVI represents highly vegetated areas of Los Angeles. Everything that's red or that has low NDVI represents areas of Los Angeles which are poorly vegetated or that have high urbanization. So this is my methodology for doing this project. In order to understand how income and drought and temperature spatial variability impact stability, I first had to calculate stability for each day of my time series. So to do this, I first calculated land surface temperature, a drought index, and NDVI for each day. And then I detrended and deseasonalized this data, which means that I took away the long-term trend and seasonal effects. I did this because I'm interested in understanding how vegetation responds to unusual conditions and not to long-term trends or to seasonality. I then took land surface temperature and a drought index for a specific day, the NDVI for the previous day, and regressed that against the NDVI for the current day I'm interested in to get my stability coefficients of resistance and resilience for that specific day. And in particular, I'm looking at resistance and resilience in terms of drought and temperature. I then took my data on median income as well as drought and temperature spatial variability and regressed that against my stability coefficients to get data on how income and abiotic variability in Los Angeles influences stability. So this is the actual equation I used to calculate stability in Los Angeles. Y represents NDVI, and so the effect of stress on plants I measured as a change in greenness of the plant itself. So this is saying that NDVI at the current date is a function of NDVI at the previous date, where the coefficient to that is resilience. The next term is the water balance or the drought index, and this is defined as precipitation minus potential evapotranspiration, and the coefficient to this is the resistance to drought stress. And the next term is the land surface temperature at the current date, where the coefficient to this is the resistance to temperature stress. And then there's the error term. So I'll show you some data of how these terms vary over time and spatially. Everything above the zero line means that it's greener than the long-term average. Everything below means it's less green than the long-term average. And this is looking at NDVI over time. I want to point out the 2 dates here. You can see that there's a lot of spatial variation within the city itself, and there's a lot of variation between the 2 days. Everything that's yellow in the images means that it's greener than would be expected from the long-term average or from seasonal effects. Everything that's blue in the images indicates that it's less green than would be expected from the long-term average or seasonal effects. This is land surface temperature over the 17-year time span. You can see that the land surface temperature varies somewhat randomly around the long-term average. But again, for any specific date, there's quite a bit of variation within the city. Again, everything that's yellow is warmer than would be expected from seasonal effects or the long-term average, and everything that's blue is cooler. And then here's drought. I'll show you this as a little video. There it goes. Awesome. So I flipped the color bar for this one, but you can see that everything is blue is wetter than the long-term average of what would be expected from seasonal effects, and everything is yellow is drier than the long-term average of what would be expected. So you can see, I just want to show here that there's quite a bit of spatial variability within Los Angeles itself over time. Some areas are drier and wetter, but there's no consistent areas that are always dry or always wet. And then the long-term average seems to vary quite a bit around the long-term mean, which is 0, with some periods definitely wetter and some periods definitely drier than the long-term average. So it looks somewhat cyclical in terms of the long-term trend. So the ones I was able to get all my data for land surface temperature, the drought index, and NDVI for my time series, for the 17-year time series, I was able to use the equation that I showed you to calculate the stability metrics. So this is stability for Los Angeles of July 24th of last year, with resilience on the left, drought resistance in the middle, and temperature resistance on the right. And so everything is yellow in the graph represents vegetation that is more stable or more resilient or resistant to stress. And everything is blue in the graph represents vegetation that is less stable or less resilient or resistant to stress. So for instance, looking at the middle graph, which is drought resistance, the yellow indicates that if vegetation is in that location, that it will be more resistant or would be able to maintain function more readily under conditions that are drier than average. I want to emphasize, however, that stability does not equal high provisioning of ecosystem services. You can have vegetation which provides a low amount of ecosystem services but is stable. So stability is simply referring to the fact that vegetation will either provide a function or the vegetation will either be similar or dissimilar to how it's been in the recent past. So either it would be stable or unstable. My data also showed that there's a correlation between resilience and NDVI in the recent past, and so plant productivity. So my data indicated that if plants are productive yesterday, that they're better be able to respond to stress today. And if plants are not productive and not healthy yesterday, then they will be able to take much longer to respond to stress today. Again, I want to show
the top of each one of those 3 graphs because I can't see it.
Sure. So on the left it's resilience, in the middle it's drought resistance, and on the right is temperature resistance. And so looking at this, you can also see that there's quite a bit of spatial variability. The spatial variability over time in Los Angeles of the stability metrics changes in a similar way to the drought graph that I showed you previously. And so my question is, what drives this spatial variability? What are the factors that influence spatial variability of stability metrics in Los Angeles? And so once I was able to get my stability metrics, I got my data for the factors that I'm hypothesizing influence stability. So this is median income in Los Angeles in 2015 from census data by census tract. And so following my hypothesis, I would expect that areas with higher income or that are in the deep purple would have higher stability than areas in the lighter purple. I also got data on the variation of drought and temperature throughout Los Angeles. And so this is looking at the standard deviation of drought and temperature within 9 pixel squares throughout the city. So this is basically asking whether 1 pixel of drought or temperature is more similar or dissimilar to its neighbor. This specifically is looking at the variation of temperature on June 20th, 2015. And you can see that the urbanization really pops out from this. So this is indicating that there's more variation in temperature on this date in the urbanized portions of Los Angeles than in the less urbanized portions of Los Angeles. Areas of the city which may have more spatial variability in temperature could include places with rapidly changing land cover or many types of land cover in a small area. And places of Los Angeles which could include high levels of drought spatial variability, could include places where an individual park isn't 100% watered, or a residential area which is near chaparral or wildlands. So finally, I regressed my hypothesized driving factors of stability against the stability metrics to see how the relationship plays out. So for all of these graphs, all of the data that's above the 0 line indicates that there's a positive relationship on the hypothesized driving factor on stability, and everything below the 0 line indicates a negative relationship. The further the distance that the points are from the 0 line indicates the stronger the relationship. Everything further to the right of the graph indicates that the hypothesized driving factor explains more of the variance in stability. Everything on the left of the graph means it explains less of the variance. So this is looking at income specifically, and I expected that increased income would lead to more stability in Los Angeles, or in other words, that most if not all of the points should be above the 0 line. That doesn't seem to be the case. There are some points below the 0 line. I think it would be interesting for future research to look into why this is happening, since I think the luxury effect would predict that increased income should lead to greater stability. As well, income itself isn't specifically a great predictor for stability, since it's not able to explain about more than 15% or so of the variance in stability throughout Los Angeles. This is drought variability on stability. Again, I would expect that for drought variability and temperature variability, that increased variability would lead to decreased stability, or that all, if not most, of the points should be below the 0 line. This doesn't seem to be the case here. The data is not cooperating with me. But this drought variability is able to explain more variance in stability than the other factors that I tested. So for the middle graph, which is drought variability and drought resistance, the points on the right of the graph indicate that for those days, drought variability alone was able to explain nearly 50% of the variation in drought resistance. And then finally, we have temperature variability on stability. Again, I would expect that for most of the points should be below the 0 line. And here it seems that the majority of the points are below the 0 line, so that is positive for what I expected. However, I think that it would be interesting in the future to look at why increased temperature spatial variability and drought spatial variability would lead to increased stability, which are all the points above the 0 line. This is the opposite of what I expected. So I think that some challenges they faced in doing this work included working with large data sets, as well as making the call between spatial variability or spatial fidelity as well as temporal fidelity, since there's a trade-off between the two. My earlier data indicated that there is a relationship between working with, or there is a relationship between resilience as well as vegetative productivity in the recent past. And my data also indicated that there is a relationship on the effect of income as well as spatial variability in temperature and drought on stability, although the effect is generally small. And that drought spatial variability has the largest effect on stability. Overall, I think that the effect of urban vegetative stability can have an important impact on the delivery of urban ecosystem services under stressful conditions for cities. Cities are stressful places for plants, and will continue to be more stressful due to the impacts from climate change and continued urbanization. And so understanding how urban vegetation responds to stress can lead to a greater delivery of services, as well as lay the framework for more sustainable cities. So in conclusion, I'd like to thank the Los Angeles Urban Center for allowing me to do this research in the first place, as well as to present here today, and as well as like to thank the Generette Lab for their helpful and constructive feedback on this project. Thank you.